Yeah, assalamualaikum and hi to all. So I'm going to continue with the second video for force convection of external for the subject of heat and mass transfer BMCG 3723. And in these slides, I'm going to explain parallel flow over flat plates. So if you consider a flat plate with a flowing over it has a length of L, and from experimental study show that at the beginning of the flow we have a laminar flow, and then up to certain distance, which is called critical distance, the flow turn out to be turbulent flow as shown in the figure. So we can calculate this Reynolds number of this laminar and turbulent flow by using this equation shown in the slide, which is Reynolds number equal to rho Vx divided by mu. Rho is the density of the fluid, V is the velocity, and X is the distance. So in engineering analysis, a general accepted value for the critical Reynolds number is 5 times 10 power of 5. This critical number is the region or the maximum distance before the laminar flow turn out to be turbulent flow. So actually in the actual value of engineering, the critical Reynolds number varied for somewhat from 10 to power of 5 to 3 times 10 power of 6. But in heat and mass transfer, we use 5 times 10 power of 5 as the critical Reynolds number. So from the Reynolds number, we can calculate the local friction coefficient. It is called local since we can calculate the friction coefficient at location X over the plate, meaning that at certain value. So we have this two equation for laminar and turbulent, and you can see we should calculate the Reynolds number first, and if the Reynolds number is below than 5 times 10 power of 5, we can use the laminar equation, and if it is above it, then we can use the turbulent equation. So as you can see in the figure on your right hand side, top figure, I put the overall length of the flat plate is equal to the critical distance, which is the maximum distance before the laminar flow turn out to be turbulent flow. So for these cases, we can use laminar equation to calculate the boundary layer thickness and local friction coefficient. And for turbulent flow is within the range of above than 5 times 10 power of 5 to the 10 power of 7. So I put a note there where if the critical distance is extremely small compared to the turbulent distance, so we can neglect it. So meaning that if the flow is the laminar flow is extremely small compared to the distance of the turbulent flow, so we can neglect we can assume that the flat plate is completely turbulent. So if these cases happen, we should use the turbulent equation. So average friction coefficient. Okay, we already know the local friction coefficient up to certain distance. Now we interested to calculate the overall friction coefficient throughout the entire flat plate. So still we have the laminar and turbulent flow, and within the certain Reynolds number. Okay, so you can just use this equation to calculate it, and then there is a cases where laminar and turbulent flow are significant, where we cannot neglect the laminar or the turbulent flow. So before this, we divide it into two. We should calculate in laminar or turbulent. Now we should consider both laminar and turbulent. So to calculate the drag coefficient or friction coefficient, we need to use the integration over the entire flat plate. So we have two, laminar and turbulent, so we should divide it into two integration as shown in this slide. where Cf is equal to 1 over L, integration over 0 to critical value, critical distance for laminar flow, plus the integration over from the critical distance to overall distance of the plate for turbulent flow. So from this integration, we get the equation at the bottom of this slide. So based on what I explained for the friction coefficient, I can summarize the friction coefficient as follow, where we have local friction coefficient for laminar and turbulent, and then we have the average friction coefficient also for laminar and turbulent, and last we have the average friction coefficient for both laminar and turbulent flow. Going to the next step, which is the heat transfer coefficient, we can calculate the heat transfer coefficient, which is the value of H, which is the convection heat transfer coefficient of convection. So from the local Nusselt number at location X over a flat plate. So you can see here for the laminar flow we have Nusselt number at distance X equal to Hx at distance X times the distance X divided by K. H here is the coefficient of convection for the flat plate, and K is the thermoconductivity of the fluid. So these cases is valid for Prandtl number larger than 0.6 and Reynolds number below than 5 times 10 power of 5. Okay. So as for turbulent flow, we have different ranges, which is within the 0.6 to 60 Prandtl number and 5 times 10 power of 5 to 7 power to 10 power of 7 for Reynolds number. And I put a note here, these relations are for isothermal and smooth surfaces, meaning that the equation that I show to you before for the local friction coefficient and local Nusselt number is for the flat plate which has isothermal surfaces, meaning that the temperature is same throughout the flat plate. So you can see here is another note, the local friction and heat transfer coefficient are higher in turbulent flow than they are in laminar flow. So you can see in the figure we have Hx and Cfx at the y-axis, and x-axis is the distance. So you can see the line, the pink line, which is the Hx and Cfx. So the value of the drag coefficient and convection coefficient decreases as the laminar flow distance increases. So up to the border of the transition, which is from laminar turn out to be turbulent, the as mentioned in the note, Hx reaches its max highest value and the flow become fully turbulent and then decreases by a factor of x with the power of minus 0.2 in the flow direction. So within the transition range, so the flow is a mix of the laminar and turbulent flow. So when it completely reach the turbulent flow, which is the border of transition and turbulent, it has the highest convection heat transfer, and then it start to decrease again with the factor of x power of minus 0.2 as shown in the notes I put it there. So average Nusselt number, we already know the local Nusselt number, so we should know also the average Nusselt number throughout the flat plate. So you can see here the Nusselt number is equal to HL. L is the overall length of the flat plate. So and the value is slightly different from the local Nusselt number and average Nusselt number. And still we have the ranges, same ranges of Reynolds number and Prandtl number for laminar and turbulent flow. In these cases also, we should consider the laminar and turbulent flow are significant, where the heat transfer convection coefficient is H equal to 1 over L, and integration over the Hx for laminar flow plus integration over turbulent flow. So from this integration we can get the equation as shown in the pink color with the ranges of Prandtl number and Reynolds number. So liquid metals such as mercury have high thermal conductivities and being used in application that require heat transfer rates. But it has very small Prandtl number, thus the thermal bond layer develop much faster. So for liquid metal, the Nusselt number is different, which is written in the black color, and the Prandtl number is less than 0.05. And for all liquid, the Nusselt number is equal to Hx for distance x, and x is distance divided by k, which is written in the pink color in the equation. And I put a note down there where PE, which is pellet number, is equal to Reynolds number times the Prandtl number, and it is a dimensionless parameter. So this is the summary of the heat transfer coefficient, where we have local Nusselt number for laminar and turbulent within the range of Prandtl number and Reynolds number, and we also have an average Nusselt number with the same ranges of Reynolds number and Prandtl number, and then we have the average Nusselt number for laminar and turbulent flow. So before this, we consider that the flat plate has a uniform or isothermal surfaces which has same temperature. Now there is another boundary condition where the heat flux is uniform throughout the flat plate. So same with the previously. So we have laminar and turbulent flow also, and with the ranges of Prandtl and Reynolds number, same Prandtl and Reynolds number for turbulent and laminar. So you put here, if the heat flux or uniform heat flux is applied, so it gives 36% higher for thermal flow and 4% higher for turbulent flow relative to the isothermal flat case. And when heat flux is prescribed, the rate of heat transfer to or from the plate and the surface temperature at this x are determined from this equation, where Q is the heat flux per unit area equal to Hx, which is the convection heat transfer at a distance x, and T as x, temperature at distance x, minus T infinity. T infinity is the surrounding temperature. From this we can calculate the surface temperature of the flat plate at certain distance x. So there is another cases where the flat plate with unheated starting length. So we can calculate the local Nusselt number, which is given for laminar and turbulent flow. There is a tau there, which is the distance of no temperature variation with the environment or the surrounding. And then we have Ts, which is temperature on the surface of the flat plate, as you can see in the figure. So the Ts is the temperature difference than T compared to T infinity, and at the delta distance, delta or tau distance, there is no temperature variation. So we have two boundary layers, which is velocity boundary layer and then thermal boundary layer. Okay. So for these cases, we should use these two equations for local Nusselt number for laminar turbulent and average heat transfer coefficient for laminar and also turbulent. Okay. As a summary for this section, so we have the heated from leading edge or isothermal flat plate, and then we have uniform heat flux with the equation, which is the overall Nusselt number, because we are interested in the convection heat transfer coefficient. So I'll put this overall average Nusselt number, and then we have the unheated starting length and with the local Nusselt number and average convection coefficient. So from these three equation, we can predict the value of H for each cases. So this is the end of second section for forced convection of external flow. To further give you understanding, you should look into the exercise. And thank you for your attention and hope you enjoy this video.